Today we're going to do the two-block problem. The two-block problem, as you may have guessed, consists of two blocks being pushed by a horizontal force. We're going to put the two blocks on a frictionless surface. Oftentimes they have different masses. We're going to call this capital M for big mass. And we'll call this one little m for little mass. We're going to push them to the right with a hand. And for make it easy, we'll say that the friction between the blocks and the surface is 0. To proceed from here, we're going to draw force diagrams for the big and the little block. We'll call the little block the green block, and we'll color it in green. And we'll call the big block blue block, and we'll color it in blue. And so what are the forces on the blocks? If we look at the green block first, what we'll notice is that the earth pulls it down. That's the weight. We'll call that little mg. The surface is pushing it straight up. That's the normal force between the little block and the surface. And to the right, there's a force from the big block on the small block. And we're going to call that the force of big M on little m. When we look at the big block, we have similar forces. We have big mg, that's the weight of the big block. We also have a normal force here. Those balance. We have the hand pushing to the right, and because it's contacting, we have the little block, the little m, pushing backward. This is the force of little m on big M. What's important about these two forces, this force of big M on little m and the force of little m on big M, is they are equal in strength, opposite direction, and they act on the other object. Therefore, they are Newton's third law force pairs. From here, we're going to want to find the acceleration of the blocks, and to do that, we're going to find the acceleration of the system. And when I mean the system, I mean both blocks combined as one object. If I think both blocks combined as one object, if I check out the force diagrams, each normal and weight balance each other out. We have the force of big M on little m and the force of little m on big M, and because they are interaction forces within the system, they balance each other out, and so the unbalanced force here is the hand. So if I start with a Newton's second law statement that the acceleration of the system is equal to the net force on the system divided by the mass of the system, we can write an expression for the net force in the system as just the force by the hand. And then the mass of the system would be the combined masses, big M plus little m. From here, we can write expressions for each, the green block and the blue block. We're going to write our own Newton's second law statements for those. So to do the green block, it's pretty easy because you only have one unbalanced force here. The acceleration of the green is equal to the net unbalanced force on the green over the mass of the green. The net unbalanced force is force of big M on little m divided by the little mass. And if we want to write an expression for the acceleration of the blue block, the acceleration of the blue block would be equal to the net unbalanced force on the blue block over the mass of the blue block. And in this case, expression for the net unbalanced force is the difference here, so it's the force of the hand minus this Newton's third law force pair, F of little m on big M divided by big M, which is the mass. All three of these accelerations are the same because the blocks are all accelerating together. And that's how you write expressions for the two-block problem.